Hello, everyone. You're welcome to our third lecture on integration. We've already looked at a couple of things, Riemann sums, what the definite integral and indefinite integrals are. In this lecture, I'm going to take you through techniques of integration, trigonometric integrals, integrals of rational functions, the reduction formula, and then finally we'll look at improper integrals. This will take a couple of videos, so this will be split into 3 or probably 4 videos. So watch out for the other videos on these slides, okay? So we want to start off with a very popular and powerful technique of integration known as the method of substitution. And so what I will do is I will state 2 theorems on the method of substitutions. I'll show the proof of those theorems, and then from there we'll do some examples to illustrate it. Okay. Now, in general, you can use this method of substitution to integrate functions if those functions are of this form. Okay, f into g of x times g prime of x dx, where g prime here is the integral of what is inside here, inside the function f. All right. So the theorem says that if u is equal to g of x, is a differentiable function whose range is in the interval I and f is continuous on I, then the integral of this integrand is equal to integral f of u du, where remember that u is g of x. Okay. So basically saying that if I replace g of x with u, I can reduce this to this form. Okay. So how do we prove that? Let's prove this theorem and then move on to the next thing. So you let f be an antiderivative of f, which means that f prime, big capital F prime is equal to small f, or big F is equal to the integral of small f dx. Okay, so we can apply the chain rule. Then d dx of f as a function of g of x can be written as f prime g of x, and then you have to multiply by the integral of the argument, or what is the inner function, right? G prime dx. So the derivative of this is equal to this. You can integrate both sides of this expression, so integrate this and that. But note that this is d dx of f dx. So if I integrate this, the result will be f g of x, right? You're going to get this. So this is equal to this plus c. Well, you could also substitute u here, right? You have f prime u, right? And then g prime dx is just du. So you have f prime of u du, right? The integral of f prime is just f of u, okay? But u is g of x, so you get this. So either from here or from there, this integral gives you this expression on the right, okay? So now I can write this guy, right, to be equal to this, the same thing I have here, and that is equal to, we know g of x is u, I can put u here plus c. That should be equal to, remember that because capital F is the antiderivative of small f, right, or big F is the same as the integral of small f, I can write this as the integral of small f of u du. Of course, if I integrate, then that is where I get my constant of integration. So this is equal to this. Basically, this is what we wanted to prove, right? Capital F prime is small f, so that is here. I have my g of x, I have g prime of x dx. This is basically the left-hand side of the expression is equal to the right-hand side, which is this. So we have proved, we have shown that the method of substitution actually worked, and there's a theorem to back that up. That is the important thing. Okay, let's quickly look at another theorem. Now, the one we just proved is for indefinite integrals. So we want to look at another version of the same theorem, but for definite integrals. So in this case, if g prime is continuous on AB and f is continuous on the range of u, then the integral from a to b of this expression here is equal to the integral of g of a to g of b of f of u du. Once again, all I'm doing is replace g of x with u. So this becomes u. If you do that, the derivative, right, this guy becomes a du. Also, if I replace x, the lower limit is a. If I put a here, I get g of a. If I put the upper limit b in place of x, I get g of b. That's what this is saying. Okay, so let's prove that and do some examples to illustrate this. So we can let, once again, f, capital F, be an antiderivative of small f. That is, capital F prime is small f. Okay, this is the same as we have before. Using the chain rule, g dx of this is equal to this expression, but capital F prime is small f, so I can write it as this. Okay, once again, I can integrate both sides. The integral of this is the left-hand side here, and now I'm going to put a limit on it. Note that if I integrate this, the derivative goes away, and I'm left with capital F g of x, and then I put in the limits from a to b. Okay, so integrate both sides. This is the right-hand side. The left-hand side here becomes this guy from a to b. Okay, and of course, I can just plug in my upper and lower limits, and I get this expression here. So basically, what we have here is that the left-hand side here is equal to this expression, equation 1, okay? Now, what we're going to do is that we want to show that the right-hand side is also equal to this expression here. And for that matter, they are equal. That's the point, okay? So let's do that. By applying the evaluation theorem, okay, remember the evaluation theorem, basically the second part of the fundamental theorem of calculus. If I integrate, the integral of this f of u du is equal to, remember that small f is big F prime. So if I integrate big F prime, I'm going to be left with big F. All right. So the integral of this is just big F of u, and I put in my limits. So in place of u, I'm going to have f of g of b minus f, and then I plug in this. Okay. So we get the right-hand side of our original equation is equal to this expression here. So now you can compare equation 1 and 2, and you know that they are equal. Okay. So, which means the left-hand side is equal to the right-hand side. So we have proved the theorem. Remember, the theorem says this is equal to this. We've shown that the left-hand side is this expression, and then we've just shown that the right-hand side is the same expression, which means they are equal. Okay? So the point of these two theorems is that the method of substitution is a powerful method which is backed by these theorems, which means you can actually apply them and use them to solve problems. So let's do a couple of problems. I have several examples here. I'm not going to do all of them. I'm going to pick a couple of them and show them, and then you can try the rest. Okay, if you're struggling with it, you can look in the lecture notes. Okay, I have solutions to I think pretty much all of these. Okay, so let's use a couple of examples to illustrate the method of substitution here. So A says I is equal to the integral x cubed cosine of x to the 4 plus 2 dx. So I'm going to substitute for this. Hold on. I'm going to make a substitution for x squared plus 2. I'm doing that because when I differentiate this, I'm going to have the x cubed pop out. All right, that is the point. So let u be equal to x to the power 4 plus 2, which implies the u is equal to, if I differentiate this, I'm going to get 4x cubed dx, which means that x cubed dx is equal to 1 over 4 du. Right, so that's the point of the substitution. You see that this x cubed and the x here becomes just 1 over 4 du. So you simplify it. So now I can reduce all the x's here into u's, and I'm going to have I is equal to the integral x cubed dx is 1 over 4 du. Cosine of this guy becomes cosine of u. So now we have an expression which is much simpler. And so we know that derivative of cos u is just sine u. So I get 1 over 4 sine u plus c. Remember to put back the original variables. The original variable was in x. So in place of u, I'm going to replace x to the 4 plus 2. And that gives me this expression as my final answer. Okay, good. Let's do B. B says I need to integrate x over x squared plus 1 dx. So again, I'm going to make a substitution for this x squared plus 1 here. Once again, the point of that is to reduce it so that x dx will sort of pop out, and then I can easily simplify this expression so that all the x's becomes u's and constants. So let u be equal to x squared plus 1 and differentiate both sides, then the u is equal to 2x dx, okay? Which means x dx, this guy's here, from here is just 1 over 2 du. So I can replace x dx by 1 over 2 du, and the lower, if you like, the denominator now becomes just u. And so I can reduce this to 1 over 2 integral of 1 over u du. Integral of 1 over u is just ln u. So I have 1 over 2 ln u plus c. Again, put back the original variables. So in place of u, I'm going to replace it with x squared plus 1. And so I'll get a solution to the original integral. So that's the solution. Okay, good. Let's do a couple more. Here, I is equal to the integral sec x, square root of sec x plus tan x dx. All right. Here, I'm going to make a substitution for sec x plus tan x. Okay. Now, this simplifies it, but it takes a couple of steps in this case to see the simplification. But if I make a substitution for this and differentiate, I'm going to have the u is equal to the derivative of sec x is sec x tan x, and the derivative of tan is sec squared x. So I get this. Okay, I can pull out sec, so I'm going to get sec x tan x plus sec x dx. Okay. Now we just said tan x plus sec x is u, right? So all of this guy is u, so I'm going to have u times sec x dx, which is this, which implies that sec x dx is equal to the u over u, right? I'm just taking this u over here. So I get this. So you see, this sec x dx here becomes the u over u, okay? So if you go back to this, I now becomes the u over u multiplied by the square root of u, because all of this is now u. And this is equal to u, 1 over u is u to the negative 1. And then the square root of u, of course, is u to the 1 over 2 du. Simplify this, you get that. And integrate this, you get this. Again, put back your u, which is sec x plus tan x, and that gives you the solution to G. Okay? Great. So you see how powerful the method of substitution is. You can basically reduce such a complicated expression into something like the integral of u to the negative 1/2 du, and then you solve it. Okay, I think this is the last one in this set of questions. We want to integrate this expression here. Now here, what you can do is that you can make a substitution for the denominator. Okay. You could try, if you want, try the numerator and see what the result is. Okay, but the point is that if you make a substitution for this, and then the x pops out easily, and you can make a substitution for them. That's why you make the substitution here. So let u be equal to 2 sine x plus cosine of x. Then the u will just be equal to, remember how you differentiate these guys. This is 2 cos x. This becomes negative 2 sine 2x. All of that dx. Okay, I can pull out 2, which I get by this, which implies that if I divide through by the half, the 2, I get 1 over 2 du is equal to cos 2x minus sine 2x dx. All right. So basically, this part is almost there. We are almost getting this, but they are reversed, right? This is a negative of that, so I have to negate both sides of this. And so I get negative 1 over 2 du is sine 2x, sorry, minus cosine of 2x dx. So now I can replace the numerator, all of it, with the x by this guy, negative 1 over 2 du, okay? And then the bottom is just u. So I'm going to have negative integral half du all over u, which can be written as this, okay? 1 over u, So I just get negative 1 over 2 ln u plus c. Again, replace u with the original variables. So I'm going to have this expression here as the solution to that. Okay. So the best thing is that try your hands on what we've just done, and then go back and try the other problems. Okay. Once again, the solutions to those problems are in my in the lecture notes, which you can take a look at if you're struggling with them. Okay, good. Let's move on to a second set. What we just did was on indefinite integrals. So there were no numbers on the limits, no lower and upper limits. Now we want to look at some examples on definite integrals. So integral from 0 to 4, for instance, of this expression, and so on. Once again, I'll pick a couple of them to illustrate the method of substitution, and you can try the rest. Okay. Okay. So let's do a couple of them. I picked A. A is this integral from 0 to 4. We want to integrate 2x plus 1 dx. The easiest substitution to do is the expression under the radical, right? So let u be equal to 2x plus 1. Differentiate that. You have du is 2 dx, okay? Which implies 1/2 du is dx. So I can replace the x here by 1/2 du. I can replace whatever is inside the radical with u. Now here, when you have, when it's a definite integral with lower and upper limits, note that this limits corresponds to x. In other words, x starts from 0 to 4. But you are making a substitution for x now. The variables are going to be in terms of u. So you need the corresponding limits in terms of u, okay? So you can use this to do that. When x is 0, u becomes 1, okay? You see that? And when x is 4, right? You put 4 here, you get 9. 2 times 4 is 8 plus 1, 9. So now the limits now becomes the integral from 1 to 9, right? U is 1 here and then 9. And I have square root of u. The x now is 1/2 du, which is this. So I can basically reduce it to this. This is easy to integrate, okay? And so I get this expression here, okay? Again, the limit is now 1 to 9. Okay. Now, there is another way you could have done this. You could have left this out altogether, okay? Okay, you could have left this substitution stuff. And then from here, leave out the limits and integrate this. So you're going to get here without this limit. And then you can put back your original variable here. So you can put 2x plus 1 in place of the u, and then use the original limits from 0 to 4. That is one way you could have done that. Okay. Sometimes it's simpler to do this, so I often prefer to do this. Okay. Okay, so once you get here, I mean, you know how to do this. You plug in 9 minus, then you put in your 1, and you get these expressions. You can. This is algebra now, so you can reduce this to 26 over 3. Okay. So when you solve A, this is what you get. Let's do B, and then D. B, our expression is the integral from 1 to e of ln x over x dx, which I can rewrite as ln x times 1 over x is the same as this, of course, the x. I can make a substitution for ln x, because when I integrate ln x, I'm going to get a 1 over x out. That's why I make a substitution for this. So let u be ln x, then du is 1 over x dx, all right? Once again, because of the limits, we want to see their corresponding u limits. If x is 1, ln 1 is 0, so u will be 0. When x is e, ln of e is 1, so u will be 1, okay? So now I'm going to integrate, instead of from 1 to e, I'm going to integrate from 0 to 1. Ln x is u, and all of this guy is du. So I have u du, which is much simpler. And so I integrate it, and I get this, and I put in my limits, and then boom, I have 1 over 2 as the solution. Okay? Great. What about D? I is equal to the integral from 0 to pi on 2 e raised to the power sine x multiplied by cos x dx. Here, I can make a substitution for sine x, all right? Because once again, when I differentiate sine x, I'm going to get this guy out. I'm going to get cos x dx. So let u be sine x, then the u is cos x dx, which means all of this guy becomes the u. And I just have e to the power u du to integrate. Now, once again, be careful to change the limits, okay? When x is 0, sine of 0 is 0, so u will be 0 as well. And when x is equal to pi over 2, sine of pi over 2 is 1, so u becomes 1 when x is pi over 2, okay? So now I'm going to integrate from 0 to 1 instead of 0 to pi over 2. And then I'm going to have e raised to the power sine x is now u, so I have e to the u. The whole of this guy is now the u. Integral of e to the u is e to the u, 0 to 1. Plug them in, you have e minus 1 as the solution. Okay? So that gives us the solution to the integral by using the method of substitution. Okay, great. So we are making good progress. Let's move on to look at the integrals of symmetric functions. Okay? They can often be tricky, so keep note of them. If a function f is continuous on this interval from negative a to a, okay, negative a is a real number, okay? If f is even, now how do you show that the function is even? You do this. If I plug in negative x wherever I see x and I get back my function f of x, then the function is even, all right? An example is x squared or x to the power 4. You can try this. If that is the case, then the integral from negative a to a, f of x to x, can be written as 2 times the integral from 0 to a of f of x dx. Okay, so you can often use this trick to simplify your integration. That's why we are doing that here. If f is an odd function, okay, how do you show that the function is odd? Use this. If I replace all the x's in the function with negative x, and the result is minus f of x, then I know the function is odd. If the function is odd, then the integral from negative a to a of f of x dx is just 0. It doesn't matter how great, how complex the function here is, as long as it's odd, and you are integrating from negative a to a, or negative b to b, right? Negative 10 to 10. As long as you are integrating that and this function is odd, the result is 0. So keep that in mind. It will save you a lot. Okay. So these are some examples basically to illustrate this. Evaluate the following integrals. We want to integrate from negative 2 to 2 of x to the power 6 plus 1 dx, and then this guy. So let's see. Here our function is given by this. All right. Now, because we are integrating from negative 2 to 2, and negative 1 to 1, we do this kind of test to see whether the integrands are even or odd functions, so that we can easily apply these things here. So whenever you are integrating from negative a to a, negative 2 to 2, try to do this kind of test to see whether the integrands are odd or even. So now, this is our function f of x. We plug in negative x into this, you get positive x out because the power is even. Okay, so my f of negative x is f of x. Therefore, f is an even function. So if I'm integrating from negative 2 to 2 of x to the 6 plus 1 is the same as integrating 2 times the integral from 0 to 2 of the function, which is equal to 2. This is easy to integrate. I have 1 over 7 x to the 7 plus x from 0 to 2. Now, it's much easier to do it this way because when I plug in 0, everything goes to 0. So I just need to evaluate at 2 instead of at 2 and then negative 2. That's why this is much easier. So you plug in your numbers and then you end up with 284 over 7. Okay? Great. And then we want to do this. Now note that this is a more complex function integrand. but we are integrating from -1 to 1. So again, you want to test to see whether your function here, right, is odd or even. The denominator is even, right? It's easy to tell that because these are raised to the power of even numbers, even integers. So that is even. So what would determine the sign, or well, to determine whether the function is odd or even, is tan. We know that tan of -x is negative tan x. Okay, you can search that up or look it up. And so this is odd. This whole function becomes an odd function. Because it's odd, and I'm integrating from -1 to 1, the result will just be 0. Okay, so if I integrate this, I get 0, just by applying those principles there, the two conditions. Okay, great. Let's see. So here are some exercises for you. You want to evaluate the following integrals. You are integrating from -a to a. So once again, you can try to apply the conditions on symmetric functions. The same thing here. So try them and see what you get. All right. So I want to end the lecture here. I don't want the videos to be too long. And then when I come back, I'm going to continue from here. I'm going to look at integrals of this form. We are still going to use the method of substitution, but in this case for integrals that are of this nature. Yes, or that. How do you do that? How do you integrate them? Okay. So try your hands on what we've done, and then we can go from there.